right? 12.2.4 black body radiation. So if you've got an opaque object, opaque objects can absorb, emit, and reflect electromagnetic radiation. They do not transmit any electromagnetic radiation. So let's start with that. So opaque objects can absorb, emit, and reflect electromagnetic radiation. So these are objects that are not see-through in any way, shape or form. Then you have a black body, and a black body can only absorb or emit. They do not reflect. So when we define a black body, we define it as the perfect absorber and perfect emitter of electromagnetic radiation. Put a box around that because that's a definition that you'll need to use. So some approximate examples of black bodies, while they're not exactly true black bodies, they're sort of the closest thing to it. Stars, black holes, and a tungsten filament in a bulb. These behave like black bodies. So stars, black holes, and tungsten filaments, which are in a bulb. So when we're talking about emission, if an object is hot, and by hot, I'm not talking relative to something else, if it has some amount of heat, it emits electromagnetic radiation. So having some amount of heat basically means the temperature is greater than 0 Kelvin. Temperature is greater than 0 Kelvin, it emits electromagnetic radiation. When you make it hotter, it does two things. It emits a larger amount or a larger intensity of that electromagnetic radiation, and it also begins to emit different wavelengths. For example, let's talk about let's talk about a tungsten filament, for example, or a piece of metal. In the beginning, it's at room temperature. It's emitting some infrared radiation. We can pick it up using an infrared camera. If we begin to heat it up, it carries on emitting infrared and begins to emit more infrared. Eventually, it starts to glow. And it starts to glow red. At that point, it's emitting infrared radiation, and quite a lot of it, and it's also starting to emit visible light in the red spectrum. If we heat it up more, it turns to orange because it starts to also emit yellow light. So when it's orange, it's emitting infrared, and it's emitting red, and it's emitting yellow. Then it will turn more yellow, and eventually it will turn white. When it's white, it's emitting infrared, it's emitting your reds, your greens, your yellows, and some blues. Now, it will never turn blue, because to turn blue, it means we have to stop emitting all the previous wavelengths of light. Yeah? If you keep making it hotter and hotter, eventually it will emit violet, ultraviolet, and carry on emitting what it was emitting before as well. So let's capture this down. Objects which are hot, which means that temperature is greater than 0 Kelvin, emit electromagnetic radiation. They radiate or emit a range of wavelengths which increases, and I'll put in brackets here. When I'm saying it increases, we're talking about the range increases, not the wavelength increases. As it gets hotter. That's why metals glow in this order. So as it gets hotter, it goes from red to yellow to white, at which point it's emitting all wavelengths of visible light. Now, one thing to notice here is that the objects were radiating infrared radiation, then visible light. They were not really emitting much or any of the higher wavelengths. So the very high wavelengths were basically not being emitted, and the very low wavelengths were basically not being emitted. So in classical terms, this led to something called the ultraviolet catastrophe. So we start a new page. So the classical approximation using classical physics, Rayleigh-Jeans came up with a formula that looked at the power density of the electromagnetic radiation. And the power density was described by the temperature of the material and by wavelength. I'm going to give you the equation for the Rayleigh-Jeans formula. However, you do not need to learn it. We're just going to explore it to gain an appreciation of what the issue actually was. So the classical, in brackets, we'll put Rayleigh-Jeans. Suggested that lower wavelengths, which means high frequencies, things like violet, ultraviolet, X-ray, and eventually gamma, were radiated more. So the equation for the power density was given by this. And we'll put that in a dotted box. So while it's a very important formula in physics, it's not something you need for your A-levels. We're just going to look at it to gain an appreciation for the problem at hand. Now, the formula gets bigger, so the power density gets bigger if temperature is increased. That makes sense. If you think of infrared cameras, for example, as things get hotter, they become brighter on an infrared camera because they're emitting more infrared. And then lambda, we can change the value of the wavelength to see how much of each wavelength is being emitted. And the formula suggests that if we make lambda very, very small, that the power density should start to increase or get very, very large because it's proportional to 1 over lambda to the 4. So if we look at that on a graph, if we put rho and lambda, very, very small wavelengths should result in a very, very large power density. So it looks something like this. Looks like a 1 over 4, 1 over x to the 4 graph. Now, doing it experimentally, when we actually do experiments and sort of measure the amount of radiation coming off of things, it ended up looking like this. Where these 2 points here were visible light. So, this was the ultraviolet catastrophe. The classical model suggested that very, very low wavelengths, that ultraviolet, X-ray, gamma ray, should be emitted more than the visible light. It suggested that the lower wavelengths should be emitted a lot more when actually, when we looked at it experimentally, we realized that those lower wavelengths were not being emitted, or very little of them were being emitted. So the largest amount of electromagnetic radiation emitted by some hot object was, in fact, visible light. That's what it was mostly emitting. And it was emitting a little bit of ultraviolet but not that much. So this was a big problem, and this was solved by quantum mechanics, quantum physics. So the dotted line, this is the Rayleigh-Jeans approximation, and the dotted is experimental. However, if you look at very long wavelengths, the experimental and Rayleigh-Jeans agreed with each other. Only at short wavelengths did they not. So this suggested that short wavelengths, such as UV, would tend to infinite power density. In other words, it shot up to infinite, so infinite amount of emission, which was not true. That's not what was happening. So this problem was resolved through Planck's work. And Planck's work fixed this problem by changing the way we think about light from electromagnetic radiation to photons. So he said that radiation was emitted in quanta, which just means photons. So instead of continuous waves, it was as short packets of energy or small wave packets. And each quanta of energy was related to a certain frequency. So a quantum is related to a single frequency. And that energy quantum is HF. So for higher frequencies of radiation, they have to be emitted in higher energy packets. So again, the issue was, with the Rayleigh-Jeans, is that because it was continuous waves, the energy of the wave related to its intensity rather than to its wavelength. But now we know that shorter wavelengths actually carry more energy with them. So at those higher frequencies, if there isn't enough energy, they're simply not emitted as much or at all. Because now the frequency is related to the energy, not the intensity. So, higher frequency radiation is emitted in larger packets of energy. The full story is actually a lot more complicated than this, but it's beyond the scope of A-level physics. So at A-level physics, we're looking at a simplified version of the events, But the appreciation here is that the classical model fell short when it came to experimental evidence, because it suggested that ultraviolet should be emitted in extremely large quantities. In reality, the experiment showed it wasn't. Work on quantum physics and quantum mechanics then changed the model of light from electromagnetic radiation to the photon model, so in energy packets. And if emitted in energy packets, then energy was related to the frequency. The energy was also related to the temperature, so if it was hotter, it had more energy to emit. So, if it's emitting energy, then the amount of energy it emits in each packet depends on the frequency. So the lower frequencies, each packet emitted by them carries more energy with it. So you would have less of them being emitted, because otherwise you're making energy from nothing. Start a new page. We'll recap next the photoelectric effect.
So with the lower the frequency, the higher the energy packets will be.
No, the lower the frequency, the lower the energy packets are. E equals to HF.
But then there'll be more packets.
There'll be more packets emitted. So the intensity of them will be greater. So that's why visible light has a higher intensity, and ultraviolet was basically nothing. So we're going to do light as a wave on one side, and light as a photon on the other side. So we go back to what the photoelectric effect was. You have a gold leaf electroscope, and you charge the gold leaf electroscope. You shine some ultraviolet light onto the zinc plate on top, and you observe that the gold leaf collapses. The explanation is that as it was charged, the gold leaf was being repelled due to excess charges, which are electrons, being stored on the leaf. When you shone the ultraviolet onto the zinc plate, that caused emission of electrons. So electrons were absorbing the energy, and then they were being liberated. And if the electrons left the material, then the gold leaf lost its charge, and then it collapsed under gravity back to its original position. So the ultraviolet light was liberating photoelectrons from this material. The experiment was done in many different ways, so we can shine different colors of light. For example, we shine some visible light, maybe green light or red light, and we see that the red light or the green light did not liberate the photoelectrons. It did not cause the same effect. You try making the red light or the green light brighter, thinking that if we increase the amount of energy, then it's going to do the same thing. And again, you get a null result. It did not cause the leaf to collapse. It did not emit any photoelectrons. So it was found that the experimental evidence suggested that the wave model was incorrect and the photon model was correct. And that's what we've accepted so far in our A-level anyway. So we're going to list what would have happened in the wave model and what did happen in the photon model. So light as a wave, any frequency should liberate photoelectrons. In the photon model, the frequency has to be greater than the threshold frequency. For wave, we should expect to see a time delay before the photoelectrons are liberated. So it should take some time. To absorb light and liberate photoelectrons. The experimental evidence showed, again in the favor of the photon theory, that the photoelectrons were liberated instantly. For any radiation above the threshold frequency. The wave model suggested that the kinetic energy of the electron should depend on intensity, or the brightness of the light. The photon model, which was the correct model, and experimental evidence showed that the kinetic energy of the photoelectrons only depended on frequency. And instead showed that increasing the intensity simply meant that more photons were emitted per second. So we'll draw what was happening. We have a material that has excess electrons. Photons are incident on the material. When the electrons absorb these photons, they are liberated and they're given some kinetic energy. So we'll recall Einstein's photoelectric equation. Which tells a story of what happens here. The energy of the photons, which is given by HF, liberates the photoelectrons, so it has to do work against the work function. So the energy of the photons, HF, liberates the electrons, so the work function, and gives them kinetic energy. And we can write this in the alternative form, which is hc over lambda is equal to phi plus ek. Let's start a new page. So we're going to look at work function and stopping potential. So first we're going to start with the work function. So to find phi, which is work function. The work function is defined as the minimum amount of energy required to liberate a photoelectron. So phi is the minimum amount of energy from a photon to liberate a photoelectron. And phi depends on the material used. So phi depends on the metal. So different metals will have different work functions. We can imagine this as an energy well with an electron in its energy well. And the energy that we need to overcome is the size of the well. So this is phi. We can represent it in two things, electron volts or just in volts, because we're talking about the electron anyway. It can also be represented in joules, but because we're talking about such small things, that's why we invent the electron volt. For very small energies, we use a different unit to make it easier. So we start with a low frequency. And then we change the frequency until we just about start getting photoelectrons emitted. That then gives you your threshold frequency. And at the threshold frequency, you just about supplied enough energy to liberate the electrons, but not enough to give them kinetic energy. Or in this case, if we're doing it experimentally, it'll be insignificant amounts of kinetic energy, so we can approximate it to be 0. So at threshold, H times F naught is equal to phi, and then plus EK, which is 0, so we just drop it. So HF naught is equal to phi. EK is 0. Now say we want to, at some point, find the kinetic energy of these electrons, how much kinetic energy they're being emitted with. We take that material and we put it into an evacuated tube. We put a voltmeter across it. And an ammeter. And then connect it to some power supply. So essentially what we've set up here is we've set up a power supply that could apply a potential to these plates. But because it's set up as a potential divider with a rheostat, if we were to slide the rheostat slider all the way to the right, that would then give us a short circuit, meaning that the plates get zero potential difference. If we slide it all the way to the left, then they get maximum potential difference. So what we do is we shine some photons or some light onto this plate. That causes photoelectrons to be emitted. And these photoelectrons flow to the second plate. And we get a reading in the current. Then what we do is we start to increase the potential difference across the plates. And we increase it until the reading of current drops to 0. If it drops to 0, it means that we've applied a large enough potential difference to the plate such that the electric field has done work on those electrons, QV, that have overcome the kinetic energy of the electrons. So at that point, the photons had to do work against the work function and work against the electric field we've applied in order to liberate the photoelectrons. So if we've managed to stop the current, it means we've stopped all the kinetic energy of those electrons. So we increase V, slide that to left until we get 0 current. If we get a 0 photoelectric current despite shining these photons onto the plate, it means the electrons have been stopped. If they're stopped, it means their kinetic energy was stopped. So their kinetic energy at that point, at the point where you just about got 0 current, photoelectric current, means that the kinetic energy is equal to the work done by the electric field QV. And the charge here is the charge of the electrons. That value of potential difference you measure is the stopping potential. So we'll call that Vs. Measured in volts. So if you wanted to find the kinetic energy of those electrons, because we can't measure their mass, because we can't measure them directly, we can use QV and get their kinetic energies. Finally, we'll look at some graphs before wrapping this topic up. So we start a new page. We'll do graphs. So electrons are stopped if they lose all EK. They lose all kinetic energy. So if they lose all their kinetic energy, then they lost their kinetic energy because of that electric field. So Ek is equal to E times the stopping potential. And if that's the case, we can substitute that back into Einstein's photoelectric equation. So we've got HF is equal to the work function plus EVS. Now we can find Vs by using graphs. So we can do two graphs. The classic one that you remember from last year, where you've got Ek on the y-axis, frequency on the x-axis, gives you a straight line for a material, gives you a parallel straight line for a different material, each of them with their corresponding threshold frequencies, and by extrapolating that to the intercept, we get minus phi. The gradient gives you Planck's constant. So these are different metals. And gradient is equal to h for both. But what did we say? We said that kinetic energy was equal to EV. E is just a constant, so we can change this graph by dividing everything. So we've got EVS equals to HF minus phi. If we divide everything by E, and then we plot another graph, we've got Vs equals to HF over E minus phi over E. And we've got a similar looking graph. We've got V on the y-axis, frequency on the x-axis. Again, we've got threshold frequency. And extrapolating that down, we get minus phi over E. So from here, depending on what frequency we use, we can read across the graph and know what the stopping potential for that frequency of photons are. And that's the end of 12.2.4.